Okay, I just wanted to prepare another little video tutorial for you guys because I know your next assignment involves quite a bit of phase 2 simulation. I already prepared another little tutorial for you, but I think it's worth going over especially a bit more the topic of boundary conditions and initial conditions for simulations. It's a little bit tricky, and I think it's worth spending just a little bit more time on that. So, to start off, when we do any kind of finite element type simulation in geomechanics, we're typically simulating quite a large area. We're talking about problems in the earth, an excavation or a tunnel, the area around that, or what we call the model domain, is quite extensive. It goes on and on and on for a long way. So we can't really include all that into the simulation. Essentially, the model domain has to be zoned with a number of mesh, with a mesh full of a number of elements. And the more elements that you get in it, the more computational effort it takes and time it takes to carry out that calculation. And it tends to be an exponential relationship, the relationship between how many zones you have and how long it takes to run. In other words, if the model gets too big, it just blows up and really won't solve for you. So you have to come up with a balance of how tight or small of a model you can make and still have enough zones to get a good, accurate solution for your engineering problem. So here's an example here of the ground surface. And in this case, we're just looking at simulating a circular tunnel. And you can see we just truncate the earth or the ground to get a model domain that is of suitable size for the simulation. And the way we account for the continuous nature of the earth with this isolated model domain is by applying suitable boundary conditions to the sides of the model that simulate this larger extent in reality. So there's many types of boundary conditions. There's deformation boundary conditions, load boundary conditions, and free boundary conditions. Here's a couple of them over here to the right of the most common ones. Right here we have a boundary condition called roller boundaries. See these circles? And that, in this case, means that the model is fixed in X. So the model, each one of these circles represents a node. The model is free to move up and down in Y, but is fixed in X. By the way, we can also apply these horizontally, where it will be fixed in Y, and rollers will allow it to move in the X direction. Either one is fine. But the bottom line is it prevents movement in one direction, but complete freedom to move in the other. Another type of boundary condition we refer to as a pin, and it is represented by these triangular elements. And each node is essentially fixed in X and Y. It cannot move in any direction. So it's completely held rigidly, the model boundary. Another thing to talk about at this point is the different types of boundaries. So we have artificial boundaries. And so in this case, we're arbitrarily selecting a boundary just so that we can constrain the size of our model to something suitable. But there are also real boundaries, such as free surfaces. So the ground surface would be a real boundary. It's a free surface. Another type of real boundary would be the inside of the tunnel. That would be an internal boundary. And it's also a free surface. In addition to that, we might have a foundation with some loading that we want to include, or whatever else. So boundary conditions are one part of the issue. Initial conditions are the other. We talked a lot about something called in situ stresses. which is the stress field in the ground. And we all understand how important they are for carrying out analysis of underground excavations. So this image on the left here shows sort of a typical stress configuration. We have a vertical stress and a horizontal stress. And we use the K ratio, or the ratio of horizontal to vertical stress, to represent those stresses. And typically we might say the stresses, say at 100-meter depth, have a horizontal stress of say 10 MPa and a vertical stress of say 5 MPa. So we use explicit values. Another condition though we might want to account for is if we have a ground surface, we know that the stresses increase with depth, and our simulation might require that we include that stress gradient due to gravitational loading into it explicitly, and there's ways to do that. So after you have your initial conditions set up, in most models the next thing to do is to follow that with changes in the model boundaries or stress conditions, like carry out an excavation, which is introducing a free boundary surface, or filling in some kind of slope or dam or embankment, or increasing the load with a foundation. So this is a typical model domain here. And you can see we have a circular tunnel in the middle of our domain, and in this case we have fixed all the boundary conditions in X and Y so it can't move. So this is an artificial boundary that is just truncating the extensive rock field and replacing it with these fixed boundary conditions. So, when we're deep down underground, say several hundred meters, and we're looking at a fairly small excavation here, this one is about 4 meters in diameter, the gravitational component is quite negligible relative to the overall stresses at this depth. So the horizontal stresses might be 2 or 5 or 10 MPa, and the vertical stresses might be something in the same order, but many MPa. And the stress gradient due to gravity across this 4-meter diameter tunnel might be a few tens of kilopascals. So in reality, including the gradient due to gravitational loading in this simulation is really negligible. The couple of tens of kPa have little effect on the stability relative to the several MPa of stress that we're going to have on this tunnel. And so we usually neglect it and just use a uniform stress field. So the same horizontal stress across the whole domain and the same vertical stress across the whole domain. And that is an efficient way to get an suitably accurate solution. So this is an example of a simulation where the boundary conditions are simply too close to the tunnel. So in addition to figuring out what depth we are from the surface and so on, we have to figure out how far the boundary conditions should be away from the tunnel or whatever excavation you're simulating at a minimum without starting to impact your results. So you can see here we have a 4-meter diameter tunnel, and the boundary is probably looks like 2.5 diameters away or something like that. Maybe it's only 2. But you can see that these stress contours clearly intersect the boundary of the model. And so what's happening is they are having influences on the stress field. The boundary conditions are close enough to the tunnel that they are influencing the stress field, and therefore it'll influence the stress field all the way to the tunnel periphery, and the stresses that you predict will be incorrect compared to, a real tunnel under the exact conditions. So we need to have boundary conditions that are further away. And this is a good example here. So a good rule of thumb is that the boundary, external boundaries, should be something like 5 to 10 times the tunnel diameter away from the tunnel. In this case, I think it's something like 7 diameters away. And there are a few factors that influence whether it should be 5 or it should be 10. But really you can gauge it best by basically seeing if any of these contours or yielded elements or whatever intersect the tunnel boundary. Or you can also just use trial and error to move it out away from the tunnel until it has a negligible impact on the answer. But a good rule again is 5 to 10 times the tunnel diameter. So this is a little example of a trick that you can use to carry out a very efficient simulation, and that is you can use roller boundaries to simulate a plane of symmetry for a stress analysis model. So if the model geometry, in this case a square tunnel, and this would apply for a circular tunnel or rectangular tunnel or whatever, stope, anything like that, as long as conditions are the same on both sides of the problem, then you can simulate it with a plane of symmetry right through the middle. And these roller boundaries mean that this boundary cannot move in the x direction, fixed in x, but it's free to move in the y direction. And so any stresses that are acting in whatever direction on that boundary, you're getting an equal and opposite reaction, as if this imaginary side were here and pushing back in an equal and opposite manner. On the other side, you can see I used fixed boundary conditions, and also on the top and bottom. That really doesn't have much of an effect on this simulation because they are so far away from the tunnel boundary, an adequate distance, that it doesn't matter if they're fixed or rollers. Now, if I did use rollers over here, again, that would simulate a plane of symmetry as if this tunnel was way over here. And you have to make sure that they're far enough away that there's no tunnel interaction or impact of the boundary conditions on the excavation, unless you intend it to be so, like we have here with this plane of symmetry. So sometimes we actually need to include stresses from gravity. So we need to include this gradient from gravity loading and the unit weight. In that case, we also want to make use of these roller boundaries on both sides. And that is because when we carry out the simulation and apply gravity loading to the model, the elements are going to move downwards under the load of gravity a little bit. And if these were fixed in y, they would kind of hang the model up, pulling it upwards, and you get some stress concentrations and some shear stresses like this. It would want to form a bit of a trough, and that would cause a stress distribution that you just don't want. You really want a nice uniform simulation as if this boundary wasn't here and we were looking at the ground in its full extent. So I think I'll show you the actual phase 2 model here and show you a couple tricks of how to set that up. So there's two main things that you have to keep in mind to include the gravitational gradient. First, you have to set up the boundary conditions correctly, so rollers in this case. And you have to, in this case, I put a fixed conditions on the bottom, which is commonly done, but I suppose maybe you could use rollers. I think fixed is best with gravity loading. You don't really want a plane of symmetry there. Oh, by the way, one other thing. You have to make sure that you get the corner boundary condition correct. In this case, I want it to be fixed in x and y. If you had a roller here it would kind of bend down in the corners, causing some kind of funny stress distribution in the corners. So the first thing you do is look at the material properties. So we're going to use the gravity loading, so the unit weight certainly has to be correct. Also, under initial element loading, this is the main thing that you have to make sure is set up correctly. This drop down allows you to select field stresses or body forces or both. Field stresses are basically those tectonic stresses, that in situ stresses that you might include in your simulation if you just have uniform constant stresses in the model. Body forces are basically due to the forces of gravitational loading. In this simulation, we want to include both. So we make sure that we click on field stress and body force. And this is not the default, so you have to make sure you go in there and explicitly change that. The next thing we want to do is go into the field stress parameters. So we open that dialog, and the default is constant. The default is a constant sigma 1, sigma 3, sigma z, and an angle. But we want to apply gravitational loading. So the first thing we need to do is let it know what we're going to use for the ground surface. In this case, I used the top of the model, and I conveniently used a ground surface of 0 meters. We also have to include the unit weight of the overburden, and that should correspond to your material properties, which it does. 27 kilonewtons per meter cubed, or 0.027 meganewtons per meter cubed. You can also include the ratio of horizontal to vertical stress in plane, meaning the x to y stresses, and out of plane, or into the screen, which is the z to y stress ratio. So these are your K ratios in plane and out of plane. And finally, you might also want to include some component of locked in or tectonic horizontal stresses. And that would come from some kind of stress study that you've done on your site, and say you realize that you need to add 2 MPa horizontally or something like that. Anyway, we're not going to include that in this case, and we're going to leave all the K ratios at 1. Okay. So then you carry out that simulation like you normally do, and you go over to the Results tab. And first thing you want to do in any simulation is check that the initial conditions are correct and they are exactly what you intend them to be. Because if you don't have it set up right, this is first off the easiest way to figure out if you have made a mistake, because it's very simple configuration. And that'll allow you to debug it very efficiently. So I have the boundary conditions just the way I wanted, and the vertical stresses, sigma y, y, are the exact gradient that I want, 0 to about 6.7 MPa, and all you have to do is multiply the unit weight by the depth and check it. Sometimes I'll spot check it, but you can see that it's pretty clearly got the kind of uniform gradient that I'm looking for. And I also check all the other stresses to make sure they're the same. Sigma x and sigma z. And so everything is the way I intend it to be, and the model has worked out very well. You can see if I had pin connections here at this boundary, there would be some funny things happening along this interface, and you'd get kind of a trough of stresses. So this is set up effectively. And so I think that that's all you really need to know to get your boundary conditions and your initial conditions set up to effectively carry out a good simulation for your rock mechanics and tunneling problem.